Hi, I'm Matt McIntosh, and today I'm going to be talking to you about some of the climate change effects that we've been experiencing in the Chihuahuan Desert Basin. Particularly, we'll be talking about long-term declining trends in Chihuahuan Desert forage production, specifically in relation to precipitation and ambient temperature. And so we recently published this information in a manuscript in rangeland ecology and management, and I'll point you to the article there in case you'd like to follow up and read more. As we know, anthropogenic emissions of carbon dioxide have greatly increased, especially since the beginning of the Industrial Revolution in the 1850s. And more recent evidence has pointed to this tremendous increase in CO2 concentrations, particularly from 275 parts per million at that time to over 406 parts per million now, and I think it's even greater than that. I looked recently, it was over 407. And so these manuscripts and others sort of point to climate change-driven phenomenon, particularly the likes of which being called the Anthropocene megadrought. And what this means is the megadrought sort of caused by all these anthropogenic warming things, such as emissions of carbon dioxide and other greenhouse gases, all points to deleterious and negative effects on the ecology of Earth. As we know, a lot of this is sort of better understood for cropland-based systems as opposed to in our extensive rangeland-based systems, and so site-specific evidence sort of pointing to the impacts of climate change are needed, particularly in our desert ecosystems. In addition, sound procedures have been developed for stocking rangelands, for instance, like calculating stocking rates and how to identify how much grass you have out there. But those all sort of depend on accurate estimates of forage production. Particularly in the paper, we talk about this manuscript by Kumalo and Holacek in 2005, and they were able to regress sort of the sum December through September mean precipitation against the sum perennial grass production annually, and they found a very strong relationship, and we'll talk about that in a little bit. So the primary objectives of our paper were to see if there was differences in precipitation and drought frequency, daily temperatures, both mean temperatures and mean maximum temperatures, and perennial grass production between sort of two time periods. So the extent of the study is from 1967 to 2018, so it's a 52-year study period. And what we ended up doing in one instance of the paper was to split the study period in half. And that was particularly based around the fact that beginning in 1993 or the early 1990s, we started to see a long-term decline in forage production, and also these sort of anomalous climatological patterns. So for instance, hotter annual temperatures and less and more sporadic rain. And all of that corresponds to, what multiple other models predicted, have shown, and other individuals, in the desert have shown. And that's all that a lot of the CO2-based warming has sort of begun to exacerbate in the early 1990s. Then we also wanted to look at the effects of vegetation phenology, so if green-up dynamics changed over time. And so we used the data set that I'll talk about in a little bit that overlapped our study period from 2001 to 2014. And we also wanted to see if these climate and vegetation trends were related, obviously. And so the study area took place at the Chihuahuan Desert Rangeland Research Center, which is in the northern Chihuahuan Desert. It's a research center owned by New Mexico State University. And in particular, this was in one study pasture So it was 1,267 hectares. And it consisted mostly of sandy ecological sites. You can see it ranged from shallow sandy to deep sandy, but the majority is sort of just in the sandy ecological site. And so you can see in the background sort of a little bit there, those are the Doñanas, and this is actually a photograph of some of the forage in that pasture, and the Organ Mountains are behind the Doñanas there. Our primary forage species is black rama, as well as some drop seed species and also some Aricida species. And then the other dominant vegetation in the site is, of course, honey mesquite, as is typical of most of the Chihuahuan Desert. And historically, perennial grasses sort of compose between 40 and 50% of the pasture composition. And woody plant canopy cover is sitting around 10%. And so an important note is that several publications have shown that if the canopy cover is not in excess of 15%, then it probably isn't having a strong relationship on grass. And so one of the things we're thinking here is that our canopy cover is not enough to impact grass, and so it's probably not a compounding factor when we're looking at the climatological impacts on the grass production. Regarding climate, the Chihuahuan Desert in general, and especially the northern part where we're located, has about 200 frost-free days with an annual mean temperature of about 14.1 degrees Celsius. The mean maximum temperature is around 24.9 degrees Celsius, so only about 76.8, sort of historically almost Mediterranean. The greatest monthly mean temperature occurs in July, and that's around 29.8 degrees Celsius. And the annual mean precipitation sits around 228.6 millimeters, so right around 9 inches. Our summer monsoons have historically produced most of our rain, which is around 44%, and they typically start around July 4th and then end sometime in October. So this particular pasture 1 at the College Ranch, or the CDRC, was lightly stocked since 1927, basically at the formation of the ranch, which occurred as a result of the Morrill Act. And so this is NMSU's sort of land grant tenure system. We, between the 1930s and 1940s, the stocking rate averaged about 40 hectares per animal unit per year. And then there was a mega drought in the 1953 to 56 period. It's very well known. So those pastures had to unfortunately be destocked with that. And then when the ranch was eventually restocked, sort of since 1967, the stocking rate averaged about 67 hectares per animal unit per year. It's probably decreased since then. Our procedures for collecting perennial grass production values basically relied on fixed transect locations. So from 1967 to 94, we evaluated 92 fixed transects that were 67 meters in length with 5 by 6 centimeter plots. So we're sort of clipping everything at that level, to the crown of the plant, drying it in the oven, and weighing it for subsequent biomass, with the reduction of wet matter. But from 1994 to 2018, our methodology changed a little bit. So we evaluated 10 fixed transects that were 100 meters each. And we had 10 subplots on those transects that were 0.5 by 0.5 meters. And just to ease your mind, we did overlap those two methodologies for a 9-year period to make sure that one was comparable with the other. And the R-squared for that is about 0.82. So fairly strong relationship between the two clipping procedures. And what's important about that is, since we're using those two things to represent the whole study, we want to make sure that they were comparable to one another. So of course, in both instances, the forage was clipped and dried, and then we determined the kilograms of dry matter per hectare by scaling up the amounts collected on the transects, obviously, to a pasture size. Additionally, there are 4 rain gauges located throughout the pasture, and this is super important because there's a very heterogeneous rain pattern in the Chihuahuan Desert. The temperatures for the study were collected daily at the Ornata Experimental Range headquarters, which is about 17 kilometers northeast from our study site. And then we extracted CO2 dry air mole fractions from the NOAA lab in Mauna Loa, Hawaii. They were very nice to share those with us. We also looked at vegetation phenology, and so what you'll see here on the right is a GIF, actually, provided by NASA Worldview. And so the red sort of rectangle shape, polygon if you will, represents our study pasture, and you can see the vegetation sort of greenness changing through time. And so this is just a snippet of the study period, and this is sort of representative of what the MODIS satellite imagery looks like after it's been filtered. So we used MODIS 16-day, 250-meter normalized different vegetation indices from January 2001 to 2014. You can see the MODIS satellite is also on the top right corner of the screen. So we download those data from NASA, and then we used this R code called TimeSat that was developed by Janssen and Eklund and also used by Browning and others in 2018. And it's used to evaluate sort of annual green up metrics. And those metrics include the growing season start and end dates, the length of the growing season, the middle date, as well as the peak value, the amplitude of greenness at the start, end, and base level values. And so here's sort of an overview of what the study looked like. So on the x-axis, you can see years running from 1967 through 2018. On the secondary y-axis to the right, you can see the temperature, and so the small triangles with the solid line represent the mean annual temperature, and you can see those are kind of sitting around that 15-degree mark, and then the mean annual maximum temperature is a bit higher, above 25 degrees centigrade, and there you can see sort of an upward trend in both examples. The same goes for CO2, which is represented by the dark heavy line with the circles all the way through. So you can see sort of an upward trend there. You can see how forage production, which is represented in the dark area in the background, is represented. And so there you can see it fluctuates greatly by year, which has been very well recorded in the Chihuahuan Desert. And you can also see how the total annual precipitation changes sort of greatly on a yearly time scale. And you can maybe even see that there's sort of a strong relationship between the amount of rain and the amount of forage. And we'll talk about that more coming up. So first we wanted to look at the changes in forage and climate variables between those two study periods. So as I mentioned, we split the study periods in half and looked at the 1967 to 92 versus 93 to 2018 time periods. And what you'll find is that I'll direct you to forage production, which is represented as kilograms per hectare. And we saw a major decrease, sort of a mean reduction of 43% in forage from 165 kilograms per hectare in that first 25-year period to only 94 in the second time period. We also saw a slight reduction in precipitation at 18.6% reduction in change, so it went from 265 to 215. But more importantly here, you'll see a minor increase in the variability. So whereas the standard error for precipitation in the first study period was 15, in the second study period was 15.8. And so we think that represents some of the increased variability that one would expect is associated with the effects of climate change. And we can talk about that more in a bit. When you look at the mean annual temperature, the third line, you'll see a definite increase of 5.9% and almost an entire degree. It went from 14.4 degrees in that first study period to 15.3 in the second. And the mean annual maximum temperature, about the same thing, only a 3.2% increase. but also changing nearly a degree centigrade from 24.5 to 25.3 degrees. And then obviously the CO2, as we mentioned, increased tremendously by 11.2%. It would probably be even greater if we had carried the study through this year. So increasing from 338.5 to 381 parts per million, which is pretty tremendous. So then we wanted to use our MODIS-derived values in the TimeSat program to look at annual phenology or greenness indices from the 2001 to 2014 time periods. And so here you'll see NDVI is on the y-axis and month on the x, and year on the secondary y-axis. I split the plot into two just for the sake of this presentation so that it's a bit larger. But what you'll see is in the first, if you look at the top left-hand corner, you see the 2001 year time period. You'll see that NDVI is fairly low, kind of oscillating around the 0.1% greenness, and the scale goes from 0 to 1, so 1 being as green as is possible. And of course, these values aren't going to be very high because we're in the Chihuahuan Desert, but what you see is sort of an average, nice long growing season, not very high peak green, but the beginning of the growing season started there in sort of mid-March and continued all the way through December. The data wasn't available for 2002, unfortunately, but for the rest of the years, you'll see basically the same trend where you see the green line is representing sort of the green up curve for that year. And so in some years, it's getting a bit higher. For instance, in 2006, you'll see it almost hits the 0.4. That happens again in 2008. Etc. And one thing to note is that the study period time is becoming, or looks as though it's shorter as you progress through time. If you look at the 2008, 9, 10, 11, 12 through 14 time periods. And so when we regress these against each other, we looked at those changes in the NDVI-derived growing season start date, for instance. Here you'll see pretty close relationship. So the R is 69% of the variation, basically, of the yearly variation. We're seeing that as time increases, that the start green up date basically becomes later. And the same goes for the end green up date. So here there's the R is 0.54 with a significant p-value. And here you'll see that as time progresses, as years progress, growing season end date also gets later and later into the year, in some instances nearly into December. And so when we look at the changes in growing season length and the peak NDVI value by year, here you'll see the growing season length through time with an R of minus 0.64 is decreasing. So whereas even in the early 2000s, a lot of those values are right around the 250 day mark. By the end of the 2014 time period, they're sitting down, a lot of them around 100 or 50 days. And you'll also see a reduction in peak NDVI value in relation to the June through September mean maximum temperature. So essentially, if you look at the x-axis, we have temperatures in degrees Celsius and the peak NDVI values on the y-axis. And what you see is a pretty strong negative relationship where the R is minus 0.81, and there's a pretty strong reduction in the amount of greenness in relation to temperature. And so we're thinking that as climate change becomes worse and these temperatures become, especially the summer temperatures become hotter and the droughts become worse, it's going to have a negative effect on how green the grass can become. When we look at some of the forage and climate relationships, so for instance, forage production and that December through September total precipitation, as Kumalo and Halachek 2005 previously had, here when we redid this relationship versus theirs, which was nearly R squared of 80%, here we have 0.49, so a pretty good sized reduction in the amount of estimable forage production. But what's important is that still 50% of the variation in forage production per year can basically be described by the December through September sum total precipitation. in millimeters, which is represented on the x-axis. When we look at the annual impacts of summer mean maximum temperature, so May through September, we also see a fairly strong negative reductions or relationship. So whereas, obviously more grass or more precipitation results in more grass, here we see that as temperatures are warmer, we can grow less grass. And so when you put those two variables together, I think it's really telling and really interesting. Here on the x-axis, you have that May through September mean maximum temperature in degrees Celsius. And then on the y-axis is the December through September precipitation sum total. And what you basically see is a reduction in grass as temperatures become hotter and precipitation becomes less. And then in years with more precipitation and cooler temperatures, you basically see more grass production. And what's significant about this is it doesn't take a rocket scientist to recognize that obviously more rain and cooler temperatures grows more grass, but as the effects of climate change become worse through time, and we see these increased mega droughts and more sporadic precipitation, which is likely going to be displaced into later times of the year, because the summer temperatures may get to a point, if they haven't already, that they're causing rapid evaporation or even rapid convection. And so the storms are sort of blowing off and we're not getting the rain that we used to. It's going to become a worsening effect. And you can see there that the May through September mean maximum temperatures sort of peak off at 34. And I think in the last couple of years, we're already seeing sort of average mean maximum temperatures well within that range. So of course, the management implications are that our results support the major climate models and that they show obviously this increase in temperature and CO2 through time. They show a potential increase in the variation of precipitation through time, and they definitely show a reduction in the amount of grass and a change in the growing season dynamics, where we're seeing green up happening less often and later into the year. Obviously, this forage decline by 43% on average between those two time periods is dramatic, and that has some really negative implications for ranchers I'll discuss in a second. Those growing seasons becoming shorter and occurring later are clearly a factor affecting the amount of forage that can be grown. And as these climate trends continue to worsen, not only will it negatively impact the forage directly because of the sporadicness of the rain and the increased temperatures, which are probably affecting the reproductive capacity of those plants' reproductive tissues, the climate change trends will also likely favor shrub encroachment. And so this means as the shrub encroachment exceeds that 15% mark, like we discussed earlier, and canopy cover and also increases the density of the plants on the landscape, they're also probably going to negatively impact grasses by effectively displacing them. And all of this means that the ranching industry is going to rapidly need to adopt sort of innovative strategies in order to stay in business, because with fewer grass resources, it's going to displace the amount of livestock that we've traditionally been able to raise on those landscapes. And so one common trend that we all are familiar with is the idea of introducing specialized desert adaptive livestock breeds or species like the Ornatas ramare criollo, or goats or small ruminants, maybe even native ungulates from others from the system, for instance, antelope. And with that, I'd like to acknowledge the New Mexico State University Department of Animal and Range Sciences, and of course the USDA Long-Term Agricultural Research Service, or not experimental range, and the New Mexico State University Chihuahuan Desert Range and Research Center, and a slew of professors and graduate students who exceeded me by a long shot in collecting all of this data and being very rigorous about this data set for the last 52 years. And so I think it's a really useful long-term data set for us to be able to analyze, and I look forward to getting some more mileage out of it. Thank you.